Okay, welcome everyone, and thank you for being here today. I know it's pretty early for some of you, but thank you for making it. Before we get started, I just wanted to let everyone know that the purpose of this recitation today is just to introduce you to the topic of CNNs and to prime you for next week's lectures. Professor Biksha will be covering all of this again in a lot more detail, so just try and follow along. Okay, so let's start by talking about what we've done so far. We've looked at a perceptron, and we've looked at the design of a simple MLP. You should have played around with this quite a bit in homework 1 so far, which I hope you're almost done and ready for submitting. We also looked at pattern detection using this MLP structure. We looked at backpropagation, and we learned how weights and biases get updated through the process of gradient descent. So what are we doing today? We're going to start by talking about why a simple MLP won't work for more generalizable tasks for deep learning, such as image classification, for example. We'll discuss what scanning MLPs are, what CNNs are, and we're going to go through some of the terminologies associated with CNNs, such as filters, channels, strides, and the whole process of convolution, some of which you might have heard before. We'll also talk about the forward function of the CNN, some downsampling techniques, as well as an intro to backpropagation during the second part of this recitation. Once again, Professor Biksha will go through all of this again in a lot of detail, so please don't panic if you feel like this is a lot. Just sit back and try to get the general gist of how things work and the overall flow. So here's the issue. We know that we can build an MLP to detect a certain pattern. However, MLPs are very location sensitive. What does that mean? Suppose you have an audio recording where the word Harry Potter comes exactly at the 5th second, and you're building an MLP to recognize that by training it on a whole bunch of recordings that also have Harry Potter at exactly the 5th second. Now, what if you want to give it a recording that has Harry Potter at the 7th or the 10th second? Would it be able to detect it? The answer, sadly, is no. The MLP is very sensitive to the location of the pattern that it's trying to detect. Same thing with memes or more generally images. Suppose you want to build an MLP to detect whether there's a dog in an image or not. So you train it on images like this one over here, where the dog is always on the left side. Would it be able to detect the dog if I gave it this image where the dog is on the right? Unfortunately not. We say that the process of having our pattern being recognizable regardless of its location is called building a shift invariant network. Basically, if the entire pattern shifts, the network should still be able to detect it. So how do we do that? How do we build that shift invariance into our network, into our MLP? What we do is that we take windows of the input, and we'll talk about how that's done exactly later, but just to get an idea, just have a look at this strip over here. So we take windows of the input, and we build an MLP that can do its job on a single window. In our scenario, its job means detecting if there's a dog in this window or not. So what the MLP is going to do, it's going to scan this window, it's going to produce an output, and then it's going to slide over to the next window to see if there's a dog in that one or not. So in an audio recording, the scan is going to be one-dimensional, while in an image, it's going to be two-dimensional. So it's going to go along the height and the width. We'll look at that more later as well. The idea here is that the MLP will produce an output for every window it scans. So it'll produce one when it's over here, and then another one, and so on. What we want to do next is we want to take a max over all of these outputs to know if a dog has appeared in any of these windows. And that's exactly what a CNN does. So you'll see this picture again next week at some point, but it's a nice visualization of what a scanning MLP does and how it would work on an audio recording. So let's say we have this recording over here, the red and purple, and we want to go through it and check the different windows to see if we can recognize a certain pattern that we're interested in. So what we do is we're going to build an MLP that looks for the pattern in the first window, and then it slides over to scan the second window, and so on along the entire length of the recording. Although we say sliding, we just mean that the same MLP will take in the second window as input. Once we've gone through the whole length of the recording, we'll then do a max function, like we said earlier, to see if the MLP recognized the wanted pattern at any point during its scanning. Okay, so before we dive into the forward function of the CNN, let's take a second to talk about what exactly it is we want to detect and how the input looks like. Let's start with images. So if we have a colored image, it's going to be comprised of 3 channels, one for red, one for blue, and one for green. And if it's black and white, we'll just have one channel. In essence, each channel is just a matrix of pixels which holds the intensity values for every point in the image. Later on, you might come across different inputs which have an even higher dimensionality of like a high number of channels, but you get the general idea. So over here we have the height, which is 4, and the width, sorry, other way around. The height and the width, which is 4, and then we have 3 colored channels. Now that we know what images are, let's take a look at how the whole process works. So first we have our 4x4 matrix over here, which is represented by the lighter colored squares, and that's our input, essentially. Then we have the 3x3 set of darker colored squares, which you can see moving over here, and it's moving over our 4x4 input. This 3x3 matrix is what we call the filter or the kernel. The filter is essentially just a set of weights. So every time we place the filter over the input, we multiply the weight of the value, the weights in that particular part of the matrix by the value of the image underneath, the value of the matrix underneath. We then sum it up for the whole filter, and we produce one value. The values produced are the ones you can see up here in the dark green 2x2 matrix. As we said, the filter or the kernel moves over the image in order to detect a pattern. So that's going to be reflected, that pattern is going to be reflected in the weights of that filter, which place more or less emphasis on particular parts of the image while scanning in order to detect the pattern that we wanted to detect. So we'll go through a more detailed example about the weights and everything in a minute. But first, let's make sure we're all on the same page for some of the terminologies. So we talked about a filter being a set of weights that can be applied to an image. So in our example over here, the filter moves right and left, up and down, 1 pixel at a time. So that means our stride is 1. The stride could also be 2 or 3 for different images and for different patterns. So technically, it's a hyperparameter that you are encouraged to tune for the CNNs you're going to be building in homework 2 part 2. We already talked about input channels, such as the red, green, blue channels for the colored images. Now, when we talk about output channels, it's essentially the number of filters applied. Now, this might be a little bit of a tricky concept, but think about it like this. In our GIF over here, the dark blue filter produces 1 dark green output every time it's placed over part of the image. You can think of this output as a processed version of the original input. So every time it goes over the entire image, we end up with an entire matrix that's the output based from that the filter produced. So let's say we had another filter, say a red filter. It too would produce its own output. That's why we say the number of output channels depends on the number of filters we want to apply to the same input. The next thing we need to talk about is padding. So let's go back to our example. Let's say we want to use a stride of 2 instead of 1, which we're using over here. Let's say we want to use a stride of 2. We can place our filter on the top left corner over here, and we'll get a value. But once we move it over by 2 pixels, it's going to hang over the input, and we're going to get an index out of range error when we try to perform our convolution. The solution to that is just to pad the image on all the sides to accommodate that. Last but not least, this formula over here tells you the expected output size for a given input dimension, filter size, stride, and padding. So in our example, we know that the width and height would be 4. We know that the kernel size is 3 because our filter is 3x3, and we know that our stride is just 1, so which is why we get an output size of 2x2. It's quite easy to derive this formula on your own, so I'll let you think about that later. Now let's take a look at an example for the forward function of a CNN. We have these weights in the kernel, which move over the image and produces a sum product of the values when it's placed above. So in this example, our input image is the one in green with the black numbers, as you can see over here, and the kernel or the filter is the one in yellow with the red numbers. The filter moves over the whole image, and at every point, it produces a single number, which is shown on the output over here in pink. So down here, we have the full calculation for the very first time the filter is placed over here, so when it produces this 4. And it's just by multiplying every number from the image by that corresponding number from the filter, and then you sum them all up, and that's what you have over here. Now, that's basically the forward function of a CNN. Some of you might be thinking, okay, we've talked about the filters as weights. What about the biases? Now, the biases are just added to the sum product over here at the pink output. So it's not really involved in the convolution. They're set for each filter. Now we're going to talk about convolution in 3D, and I'll let ID take over from here.
Yep. Thanks, Noor. Yep. So what we looked at, okay, can you hear me?
Yeah.
Okay, thank you. So In the previous slide, we looked at a 2D version of convolutions. Now, what if we have 3D images? So what does a 3D image mean is the RGB image, as Noor mentioned in the previous slides. An RGB image will have a 2D structure and it will have a certain depth, and that depth would be the number of channels. And as you can say that RGB image will definitely have three channels, RG and B. So what we do in case of 3D convolutions is that instead of a 2D kernel and a 2D input image, we now use a 3D input image, and with that we use a 3D kernel. And what this 3D kernel means is it will be a three-dimensional matrix of weights which we are going to apply to the input. And this kernel is going to have the same number of channels, that is the same depth as the input image that we have. So that is basically what a 3D convolution will do. And now this is the case of applying just one kernel to the image. If we have multiple kernels to an image, so suppose we have this image which is shown above, which is again a three-channel image. It's, let's say its size is 28 cross 28 and the depth is 3 because there are three channels in it. And if we apply four filters or four three-dimensional filters to this image, then every filter is going to produce one channel into the output. So I think it was mentioned before in this presentation, but you should remember this one key thing, that the number of channels, the number of kernels or the number of filters that you would be using in one layer is what your number of output channels will be. So number of kernels is equal to the number of output channels. This is one key thing you have to remember. I think you might be using this in homework too. Yeah. Okay, so now let's take a look at what is padding. Now, padding was also explained by Noor, but it is basically just to consider the pixels at the edges of the image, edges as in the ends of the image. Because when you're considering a kernel, let's say we have a 4 cross 4 image, and we are considering a 2 cross 2 kernel, it is going to consider just these four pixels, and it is kind of going to ignore the pixel values at the ends of the image, which is why we pad the image on all the sides with a particular padding index, and usually that is 0. And once that is done, the output image that we have also considers the information which is at the corners of this image. And usually there are a lot of ways to pad an image, but usually it is padded with zeros. And based on the formula that we saw here for the output size, we can also uh, vary the padding size based on the desired output size that we want, based on this formula down here. So you will come across this again in homework too. Next is the pooling. Now, pooling is a feature thing used in convolutional neural networks. It is kind of a layer that you add after your convolutional neural network layer. And pooling is basically used to reduce the number of parameters or to reduce the computational complexity. It is also, you can also look at it as a way to transform the images that we are sending as an input. And as you can see, we have a 4 cross 4 image here, and we are downsampling it to a 2 cross 2 image. So it can also be used to downsample, which is basically reducing the number of parameters. Now, there are three main types of pooling. One is max pooling, min pooling, and average pooling. The max pooling, what it does is, suppose we have this 4 cross 4 image and we have a 2 cross 2 kernel. We will apply the 2 cross 2 kernel on this first block, which is shown by the pink pixels. And from this particular field, we are going to take the maximum value. So the maximum value is 20, so we'll take 20. Then it will again go to the second part, and the maximum value is 30, so 30. And so on, it is going to get downsampled. Second is the min pooling. In min pooling, instead of taking the max, we are going to take the minimum of that value. So instead of 20, it would be 8 in this case, and so on. It would be a minimum pooling. And one important concept is that wherever a kernel is applied on an image, that particular region is called as a receptive field. So in this case, if I'm applying a kernel on this particular pink pink pixel square, then that is the current receptive field of our image. So that is max and min pooling. And in case of average pooling, it is going to consider the average of that particular receptive field. So if we consider the orange block, then the average of this block is 1. So we put 1 here and so on. So that is how we downsample the images. Now, one more key important factor is how do we choose which pooling operation we need to use. So if you have taken any image processing classes, then you might know, but ideally ideally how it works is that if we want to use average pooling, we usually use to smoothen out the image. So if we want to detect any sharp edges or sharp objects in the image, then we cannot detect it once we apply the average pooling, because it smoothens out the image. For max pooling, if you know, if you consider a black and white image, it goes from the pixel range goes from 0 to 255, where 0 is black pixel and 255 is white pixel. So what max pooling is doing is it's taking the max value of that receptive field, which means it's taking a value more on the side of 255. So it is used for images which are a bit darker, and if you want to make or extract the brighter features from that image, you are going to use max pooling. And on the similar way, if you want to extract darker features from the image, if an image is brighter, then you're going to use min pooling. So these are just some basics that we taught. Finally, please don't forget to submit homework part one and part two, which is due this Sunday. And I think these things are not taught in class yet, but we are just giving you a heads up to just get started with homework two, which would release this Sunday. And if you're not clear about any of them, it will be taught in depth, I think next week by Bhiksha himself. And this is all about kind of the forward propagation of convolutional neural networks. Now I'll hand it over to Tanya to talk about the back propagation of CNNs.
Hey, I'll just share my screen.
Yeah.
Okay. Can you guys see the presentation?
Yeah, we can.
Great. Hey everyone. Welcome to the second part of CNN, which is backpropagation. Let's dive right in. Okay. So just like Vedehi and Noor have talked about the forward propagation, we're going to talk about the backward propagation in CNN. Why backward propagation? Because just like we had been taught in MLPs, we want to learn the loss gradients so that we learn the weights and we can train our network. In this case, what are we learning? Let's have a look. So just like in the forward pass, we have our input X and we have our filter F. We pass it over input X. We are first going to consider the case when we are passing the filter over the input X with the stride of 1, okay? So if we consider that case, then our output would be the convolution of X and F, correct? So this is the operation that would be happening basically, where you're moving over the filter um, F over X and you're getting F11, F12, F21, and F22. Now, this was the forward pass that was talked about. So there are two things we want to find the gradient of. Can you guys tell me on chat or somebody can speak out? What are we finding the gradients with respect to?
the values of the kernel.
Can you repeat that? Sorry, G?
The value of the kernel and also the weights of the kernel.
Yeah. What about the input? What if you are convolving and you have a deep network where you have layers after layers after layers? Would you not want to learn what you're passing your kernel over as well? So,
Right, right.
right? So basically, we want to learn both the input X on which we are passing the kernel over, and we also want to learn the kernel weight. So this is basically the two loss gradients that are important to us. So we are forward propagating right now, right? So this is our node F, and we have X as our input and O as the output. We want to learn first we have the gradient of the loss with respect to the output. We will pass that back to find the gradient of loss with respect to F and the gradient of the loss with respect to our input X. So let's talk about the case where we are finding it with respect to the filter. Guys, please stop me, any of you, if you think that I need to repeat this portion. Okay, so let's have a look. So let's consider when we are, first let's consider the case where we are finding it with respect to filter F11, okay? What do we want to do? We have passed a filter over the input X. We want to find the gradient with respect to that particular portion of the filter. Let's consider F11. So we need to know all the places in the output where F11 has affected the output. So can you guys quickly tell me which all outputs F11 has affected? Anybody, very quickly, speak up.
All of them.
Correct. What about F12?
All of them
It's
again.
like all as well.
Oh, wow, you guys are smart. Yep. So basically, if we see in the presentation, then if you guys can see this portion, then F11 has affected all the portions of the output. What about the portion of the input? If you guys see F11 has affected this portion of the input, so that's what the values are here. And then O11, O12, O21, O22 are the portions of the output it has affected. So this is basically the gradient of the output that we already have with us. And we can just multiply it with the portion of the input which F11 had affected. So basically, what are we doing here? Let's try to find a pattern. Let's go to F12. Similarly, F12 had been passed over this portion. So if we multiply this portion of the input with the whole gradient, because F12 had also affected the whole output gradient, then we get the portion, then we can back propagate with respect to F12. Similarly, F21 and F22. What we are doing basically is, if you notice carefully, is we are passing the DL by the DO over this whole input. We are convolving the output gradient with the input to get the gradient of the loss with respect to the filter. Does that make sense to everyone? I want yes or no's. Vaidehi or no, could you tell me how many? I can't see it in presenter mode.
Yep.
Okay. Okay, guys, great. Now we'll move into something a little more interesting. So that's when you're trying to find loss gradient with respect to the input. When you're trying to find the loss gradient with respect to input, of course, you can see the derivatives right here, right? We want to find the derivative of from the input x11 to x33. So all of them are listed here. Let's try to find a pattern here as well, okay? Let's find, okay. So what about x11? X11 has affected which output? It's affected, we can see, 011, okay. What about x12? Let's see x12. I think it's affected 011 and 012. Probably. And you guys can see the forward pass to know that x12 had affected I think it's 011. Yeah, 011, and x12 had affected 012 and x13, and you guys can see in the forward pass to understand what all outputs it had affected. And so when we do the backward propagation, we can take gradients of those outputs and multiply it with the value of the filter, right, which had been passed over that particular input. What we notice here is that, especially when you're finding the so guys, see, you're passing this filter once here, then here, then here, then here. Then notice that for X22, there are 4 overlaps of the filter, correct? So the first overlap is with respect to the F22 portion, then it's F21, then it's F12 and F11. And that is basically getting combined and we are finding the output. So what is this exactly? Can anybody see a pattern? Can anybody draw some intuition? Anyone wants to speak up? Or in chat? Anything with respect to the filter that you see when you look at X22?
So the filter pass through X22 in all the for all the outputs.
Right. Do you see anything with respect to the subscript of the filter when you see X22?
So OIJ gets paired up with F n minus I m minus j.
Correct. So, like I have to say it simply. So great, guys, you got some intuition. So what I'm trying to say here is, if you look carefully, like we discussed before, we want to learn the convolution backpropagation, just like we did in forward, as a convolution as well. So the backpropagation is also a convolution. So here, if I look carefully, just like I had before, these are basically convolution operations of the output gradient with respect to the input, right? That's what we had understood from all these equations right here, over here. Similarly, for the input, we also want to represent this as a convolution operation. Things are not as simple as we had done when we found it with respect to the input. So be there with me. What we are doing here to get this pattern of whatever gradients that you can find here is we are taking the filter. First, we are flipping the filter and then we are inverting it. Do you guys see this pattern? F22, F21, F12, F11 here. I want a yes if you do in X22. Is that a yes from everyone?
Yes.
Okay, great. So this is what we are doing, basically. We are taking the filter, we are flipping it, we are inverting it. Next step. Oh, this gets monstrous. What are we doing here? What are these zeros for? Well, if you take... Yeah, sorry.
Could you please go back to the last slide? It wasn't...
Yeah, sure, absolutely.
So when you said we are flipping and inverting, I didn't quite get that. Is that rotation or what exactly happened here?
Yeah, so it's like first, if you do a mirror flip, how would the filter look? Would it look like this portion, the second portion, right? If you do a mirror flip.
Okay, so we flip it along the vertical axis, then flip it along the horizontal axis.
Correct.
Okay, all right, got that. Thank you.
Okay, cool. Okay, so let's come to this portion once we flip it. So this is the output gradient we have, right? what do we want to do? We want to convolve the output gradient with respect to the flipped filter that we have here, the flipped and the inverted filter. I'll tell you why this is happening and how this is working, but just bear with me. So what we are doing here is we are taking the output gradient and suddenly we are padding these zeros all around it. Whoa, why are we doing this? Well, remember that this feature map, this output feature map, has to be upsampled. Why do we upsample it? Well, have a look. When we do have an input vector on which we pass a filter over, then you will see that the resultant output decreases in size. But when we want to calculate the gradient with respect to input, what we want to do is we want to recover the input size as well. How would we do that? We can do that using zero paddings around the gradient of the output. Now, how much padding you have to do depends upon this formula that we have here, which is in our case, it would be, since our input vector is of size 3 cross 3, so it would be 3 minus 1. What is our stride size? Our stride size is 1. So that would be 2 plus, I think it's 2 into 2 plus 1. And it is 2 into 2. No, sorry. It's 2 into 2, comma 2 into 2. So that's 4 cross 4 for us. So if it's 4 cross 4, you can see this matrix and we have our gradient here. And this is our upsampled gradient with respect to the output. When we have that, now guys, look at the pattern carefully. What is happening? We have our filter flipped and inverted. This is what we will pass through that upsampled gradient of the output. When we pass this upsampled, so I wish this GIF had the zeros padded around it, which is not shown, but can you see that the filter is moving out of the gradient? Basically, it's like traversing everywhere. So this is how it's happening. It's a convolution of the upsampled loss of the gradient of the loss with respect to the output with the flipped and the inverted filter. Guys, how many of you are getting the intention? Give me a yes or a no.
We have a yes on chat.
What about upvoting? Anything? So are you guys getting the intuition? Or should I repeat? Anyone?
I
I
saw
don't
one.
understand why you need to flip the filter first. Can you hear me?
Yeah, we can hear you.
Yeah, I mean, like, before doing this step, why we need to flip the filter?
Sherry, are you there?
Hey guys, sorry, my laptop ran out of charge. Can you guys hear me?
Yeah.
Yep.
Yeah, so somebody had a question, sorry. So why are we flipping and inverting the filter, right? Okay. Tanya, can you share the slides once? Then we can be back on screen. So why, so if you see the gradient of, yeah, if we can go back to that particular slide where we were calculating the gradient right before this one. 2 slides before this one. Yeah, so if you can see x22, can you see f2 when basically if you want to find the gradient with respect to x22, let's look at O11, O12, O21, and O22. Can you see that x22 has in O11 affected has affected through the multiplication with the filter f22. In the second portion, you can see that x22 has been multiplied with the filter f21. Let's see the third equation. You can see it's multiplied with f12, and in the last equation, it's multiplied with, let's see, f11. So you see that the multiplication is with the flipped and inverted filter, and this is basically how we are able to get the gradient with respect to the input. So that is why we flip and turn the filter once, and then we multiply it with the upsampled gradient. Does that make sense now? I know it's a bit flippy, but I guess the if you can, Tanya, can you go to the 2 slides later? Yeah. So you see that this is how it is getting passed over. Basically, if you imagine this, and Tanya will also be explaining the ones cases with where stride is greater than 2, where I think you guys will develop a better intuition of how it is happening. Yes, Danish?
The terminology that's usually used in signal processing seems to be clashing with my understanding of what upsampling means. So what exactly is meant by upsampling in this context?
Here, upsampling a feature map is to increase the height and width of the feature map. So if my feature map right now is a 2x2, I am upsampling it to a size of 4x4. How am I upsampling it? I'm padding the boundaries with zeros in our case. This is what upsampling means when we talk about convolutional feature map upsampling. We are increasing the height and width here.
Right, got it.
Okay. So basically, what are the main takeaways, guys? The main takeaways are 2 things. One is that we have, whenever we are finding the loss with respect to the filter, remember it's a simple convolution in between the input and the loss gradient of the output, like we had seen absolutely in the first case. And then comes the other more convoluted case of backpropagation, where we are finding the loss with respect to the input. So you will first flip horizontally, then vertically for the filter. You will upsample the loss gradient according to the formula that's given. And then if you convolve it, you will see that the magical transition that you get all those gradients of X, which you had to actually calculate. So these are the takeaways, guys. Now Tanya will present with stride greater than 1.
I have a question. In practice, do we actually flip the kernel? Because we are flipping it every time we do convolution, right? So I guess we can just store it in the flipped manner and then just keep it as it is.
Right. So you're saying about storing it? Yeah, so basically frameworks like PyTorch, they do that implicitly. You don't have to do that externally. When you do loss.gradient, then this operation happens. But if you have to implement it using NumPy, then you can think of, while you're doing forward pass, keeping a copy of the flipped and inverted portion of the filter and using that for the backward pass. When you're calculating it with respect to the input X, you can, yes. Any other questions, guys? Okay.
Okay, so it's the same intuition if you have a stride greater than 1. So for me to explain that to you, we're going to use this example as our input. We have this input activation matrix whereby the input channels are 1 and the number of images is 1, but the height and width is 5 by 5. And then we have our filter, which is also our kernel, whereby the input channels are still 1, the number of filters k is equal to 1, and then we have a stride of 2 on both the stride of 2 on both horizontal and vertical. And then this is the output that is produced by this filter convolving with this input. So in the forward pass, this is how it will look like. Like you just go, the filter will now go, but this time it's going to, this is the first, I don't know why the animation is not playing. Okay, yeah. So sorry about that. Trying to get the animation to, I don't know if you can see. So you see how the filter moves with the stride of 2. It starts with x00 and then it moves to x02 and then moves both horizontally and vertically with the stride of 2. So you can see that it keeps one column, if that's what I can say, and then scans the next portion of input and it goes on to produce that output. So this is how the forward pass looks like for when a filter is convolving with the input in a stride of 2. So how do we get the backward pass for in that situation? And remember, in the back propagation, we assume that we already have the loss gradients with respect to the output. And what we need is the loss. The first thing that we need is the loss gradients with respect to the input, and then we also need the loss of gradients with respect to the filter. So, and remember, the loss gradients with respect to the input needs to be the same size as the input, needs to be 5 by 5, but you can see that our output is 2 by 2, meaning we need to upsample it so that it can be the same, the loss gradient can be the same size as the output. So this is the formula. It's the same formulas that have been explained in the previous part. The Sherry just explained it. And then, so here we're going to do an example of trying to get the loss gradient with respect to the input x00. So you can see this is the output, right? This is the output or y00, and the inputs that contributed to getting that output was x00 contributed to producing only y00. It did not contribute to y01 or y10 or y11. So in computing the loss gradient with respect to x00, then it's just going to be the loss gradient that it affected times the filter at that position f00, because f00 is the one that was used with x00. I hope you guys can see that from this slide. Then we also take an example of x01. x01 produced the output y00 from this equation, and the filter f01 as well was the one that was used to convolve with it. So the differentiation, the loss gradient with respect to x01 is just going to be the output, the loss gradient of the output it contributed to, times the filter position of the filter that convolved with that input. And then now we go to a special case of x02. In x02, we can see that in the first scan or the first convolving, it produced output 1, and then in the second stride, it also produced output y01. So it produced output y00 and output y01. So in this case, for us to get the loss gradient with respect to x02, we're going to sum the loss gradients of all the inputs, all the outputs that that the input contributed to. So that is going to be the loss gradient with respect to y0 times f02, which is what it contributed to, and then also we're going to multiply the loss gradient of y01 with f00 because that's the filter that convolved at that point to get that output. This is you also repeat that for all the x03, 04, you check which outputs did xij contribute to, and then from the equation you also you check the filter that convolved with that input to get the output, and then you sum all of them to get the loss gradient at that specific position. So this is an example of x22. X22, we can see from it contributed to all the 4 outputs. It contributed to Y00 here by multiplying X22 and F22. It contributed to Y01 by X22 and F20. It contributed to 10 by multiplying X22 and F02. And then it contributed to Y01 with this. So all we're going to do is we're going to take the loss gradients of the outputs that were used to calculate the input and multiply that with the filter that was used to convolve it. I hope you guys can see that. Yeah, so, but remember the output, this is our output gradients. We don't have the, and we have to have our input has to be the same size as our loss gradient has to be the same size with the input. So we have to upsample the output gradients by padding with zeros, just as Shairi explained, and then we dilate it according to the stride. So you use the same formula that was previously to find how many zeros you're going to pad up, down, left, right, and then you're going to dilate it. So this is how the upsampling is going to look like. So given that, and then the same thing with the filter, whereby we flip it, we flip it vertically and horizontally as shown. It's still the same intuition with the stride that was equal to 1. So to see it better after upsampling, now this is how the output, the loss gradients with respect to the input can be found after upsampling the loss gradients of the output. So you can see that the filter is moving to give out all this output is like a convolution of the loss gradient with the loss gradient with the graded tensor. So now that's our first takeaway, that the CNN backward propagation is identical to doing a convolution of the padded. You see, we have the upsampled gradient tensor with the flipped version of the filter. So it's like we flip the filter and then convolve the upsampled output gradient to now get the loss gradients with respect to the input. I hope that is clear. But remember, the lectures are going to be made more clearer by the professor when he gets to these topics over the next couple of weeks.
Tanya, if I may jump in, I would like to ask how many of you guys understood the portion where we are taking the gradient with respect to output and we are adding those zeros in between. So how many of you understood the dilation portion? Give me yeses or nos. Okay, so yes, there's so only a few responses out of 65 students. Come on. Okay, so many people did not understand why are we dilating. Tanya, if you would help us.
Okay, so we are dilating because we have to pad the number of zeros like on equal sides, right? But if we do that, then the input is going to be concentrated only at the center. So we also have to because the stride increases greater than 1, and maybe Shairi, you can add onto what I'm saying. If we only pad the only around the graded center, we're not going to be able to get the correct inputs loss gradients with respect to the input. So we have to dilated so that we can get the correct input.
Yeah, I think Tanya is absolutely head on. What is important, guys, notice that if you convolution with respect to, so what are we doing? Tanya, can we go to the previous slide once, please? Yeah. So what are you trying to do? You're trying to, because we are finding the convolution with respect to the input. So like what we will do, we want to flip and invert the filter and we want to pass it over like we had learned with stride equal to 1. Now, if we do this with respect to stride equal to 2, the important portion that you have to notice is it is equivalent to passing the same filter that we have, the 3x3 filter that we have, over this whole input X, just that if you see that the portions which are the row -1 or column -1 become 0. So it is the same as convolving with the filter with stride is equal to 1, but the portions row -1. So here, what is the size of our filter? It's 3x3, right? So what is column -1? It would be 2. Or what is row -1? That would be 2. So those become 0. And we club it in together. So now can we go back to the slide where we can show dilation? Yeah. So do you guys see that? So this would have been the output if we would have done it with stride is equal to 1, the middle portion. And if it's and the portions in between become 0 because they don't contribute anything to the output gradient because our stride is equal to 2. So that is why we are dilating. Now I want yeses or nos. Guys, come on. Yeses or nos, guys? Okay, great. Okay, let's move on.
Okay, so that's just the key takeaway from that is that when you're getting the loss gradient with respect to the inputs, that is the same as doing a convolution of the upsampled gradient tensor with the flipped version of filter. And remember, the convolution is always going to be a stride of 1. That is when getting the output gradient tensor. I hope that was clear. And then now we compute the loss gradient with respect to the filter, and we're going to use the same input and the same stride number. So in this situation, we have the loss gradients, the gradients with respect to the output, and what we need is the gradients with respect to the filter. So remember, to get the gradients with respect to the filter, just like we talked, when doing the forward pass, we have to check which outputs the filter contributed to, the filter contributed to. But in the backward pass, like all the filters contributed to all the outputs. So in this case, like all this, the filter that was, this filter, all of these filter values contributed to all of this output. So it's not the same like when you are checking for the inputs, which input values contributed to which specific output. For this one is all the filters contributed to, all the filter values contributed to all the output values. So this is that we're still going to use the same formula where we're going to just sum the multiplication of the loss gradient output with the loss of the filter at that time. So this is, we take an example of x00 and f00, right? This is the convolution that happens at the input where the filter is at the position of x00, x01, x02, up to x22. This is the first position. So you can see that for f00, it contributed to y00, y01, y11, and y10. So to compute the loss with respect to f00, then we are going to sum the loss gradient of y00 with x00 plus the loss gradient of y01 with x02 and plus the loss gradient of y10 times x20 and and so on, and up until we sum all of them to get the loss gradient with respect to F00. So it's the same with when you move to the second this is another example of F22. You can see that it contributed to producing all the outputs, and so we just do a summation of the multiplication of the loss gradients with the inputs that the filter was convolving at to produce that specific output. Yeah, so again, in this case, we have to upsample. No, for this case, yeah, we are doing the dilation because of the filter size, just like Shairi had explained why we need to do the dilation. And we're not going to do the upsampling because the dilation already gives us the size that is as equal as the filter size, which the loss gradient of with respect to the filter needs to be the same size as the filter size or the kernel size. So it's the same intuition on why the dilation is needed. And then after now doing the dilation, we can now see that still again, the computation of the backpropagation is actually a convolution, but this time we're convolving the input with the dilated version of the output gradient tensor. I hope people can see that. Yeah, so that's just what I just said, that when we're computing the loss gradients with respect to the filter, it's essentially, and the stride is greater than 1, getting that loss gradient with respect to the filter is the same as doing a convolution of the input gradient tensor with the dilated version of the output tensor. So we attach some articles that are going to help you understand this more. And also remember, if you don't get all of this right now, don't worry, Professor Biksha is going to cover all this over the next couple of weeks when we start learning about CNNs. Thank you.
Any questions?
So the dilution is purely caused by the stride size, right? So if the stride size is just 1, then your the filter size is going to be the same as your output size, so you don't need any dilution. So the larger the stride size is, the more you need to dilute. Is that correct? Yeah. Okay.
Yeah.
Thanks.
So if you have like a stride of 2, then you will be diluting S minus 1. If it's S, it would be S minus 1 in the column and S minus 1 in the row as well. That's how big you will be diluting it to. And it will be, of course, in Professor's lecture as well.
Got it. Thank you.
Any other questions? Everyone's clear on backpropagation? Wow.
I guess we have more questions, but however, the homework 2, part 1 comes up.
Homework 2, part 1. Oh, yeah, right. That's you have
the question has definitely come there.
Yeah, because when I had done backpropagation first and applied it, so that's why I expected more questions. But yeah, when you implement it, probably then. Great.
Well, actually, I just thought of one. In terms of implementation, does NumPy has a function to dilate the array? I know you can pad, but I'm not sure if you can dilate.
Yeah, so what is dilation? Dilation is basically, okay, hold on. That's a very great question. So, yeah. Can you see my screen? Okay. So if you see what we are doing here, consider if you have a matrix. So we had discussed, right, that we know, let's take the general case first. So here we do know just like we know how large our upsampled map will be in the case of the output gradients when we have to pad the zeros around it. In the case of dilation, you would also know what is the size of the upsample dilated feature map that you should have, right, before padding the zeros. So since your stride is equal to 2, just like I mentioned, you will be padding stride minus 1 in between, not padding, dilating, sorry, S minus 1 in between. So here we are dilating it with one row and with one column, and here we are dilating it with one row. How would you do that? Think of it as like you already knew the size was going to be 3 cross 3 because you know the stride size, right? And therefore you know what you should be expecting out of it. So once you have a matrix of say 3 cross 3, then what you can do is you can simply store the gradients in the corners and the rest would be 0. Does that make sense now?
So basically create a 0 array, in an array, and then write the values into the corresponding location.
Yeah, absolutely, right. That makes sense.
All right, makes sense.
Okay.
Actually, one more question regarding the upsample size. I didn't quite get how did we get the number 4 using the formula there a few slides ago.
Number 4. Okay. Can you stop me where you're stuck?
I mean, that's a do upsample formula, right?
Oh, right. Okay. Yeah. Yeah, that is the do upsample formula. It is a way of upsampling the output gradient so that you can get back the input.
Yeah, so height, I'm assuming is 3 because the original input has this height is 3, and then so
Right.
2 times 1 plus 1 is 3, right?
Before you ask me the whole question, give me an answer. So when you convert the output into the input, I mean, when you are passing a filter over the input, what is the size of the output feature map that you're supposed to expect? Do you have an idea about that? So say we have um simply this is 3 cross 3 and we are passing a filter which is 2 cross 2. What is the output that you would expect? General scenario, no strides, nothing. Mm,
3 by 3.
no.
You would have to subtract the filter and then divide by like you get the width
Yeah.
of your input, subtract the width of your filter, and then if you have a stride, you would have to divide by that.
Right. So exactly. So when we have an input, say H cross W, and we are passing the filter over it, then it comes with a formula which is n plus 2p minus f by s plus 1. So let me just quickly probably annotate it. So it's n, in our case, this is h minus 2p plus 2p, sorry, minus nf, which is my filter size in this case, by s and plus 1. And this goes similarly for width as well. So in our case, if we have NHRW as 3 cross 3, because you can see it's 3 cross 3, and we don't have any padding in the input, so this becomes 0, and this is 3 in our case. And this is, I think it's 2, and our stride is 1. So basically, the output feature map that we would get with respect to the height portion would be 2, right? And similarly for the width, just replace whatever the width is. In our case, it's 3 again. So then the width would be 2. So the output feature map that we get is 2 cross 2. Now, so therefore our loss gradient is also 2 cross 2, right? But what you have to do is you have to get back your 3 cross 3. So this is what we are doing here. When we are, I have to, I guess, stop annotating to move forward. So I will So this is what we are doing here. We are basically, we are basically going backwards so that we can recover the size of 3 cross 3. Is that making more sense now?
Yes, I understand the reason. Yeah, I just wanted the formula. So how do we get 4? 4 by 4.
So your input is 3, right? Your input is 3, and your stride is 1 in the first case. So if your input is 3, then 3 minus 1 is 2, and your stride is 1. So that is 1, and then plus 1. So then you would get 4 cross 4, I guess. I'm not so sure. This
height is 3, right? 3 minus 1 is 2. 2 times 1 is 1, plus 1 again is 3.
Oh, I think it should be s plus 1. Like this, there should be a bracket here.
Oh, okay. Okay, sure.
Yeah. Sorry about that. We'll fix it and upload it. Yep. Thank you for that.
All right. Okay. Okay. That's the source of my confusion. Yeah.
Oh,
All
great.
right. Thank you. Yeah.
Any more questions?
I have a question.
Sure.
So you mentioned when we do the dilation, one thing that we could do could be to save the corners and like place them in a bigger matrix and so on. So what would happen if we have sort of a bigger output losses
Let's
shape?
go there. Yeah. What happens if we have a bigger output feature map?
Yes. Is there any quick way to like filter every other thing or like jump in steps, or is that for us to figure out?
I cannot get your question. So are you asking if this was not a 2 cross 2 feature map but a 3 cross 3 feature map, how I would map it back in an easy way?
Kind of, yeah.
Yeah, so basically if you've got this 2 cross 2, then of course when even professor presents, then you will know the size of the upsampled matrix, just like the formula that I have mentioned here. You'll get a similar formula which will make your life easier to know the size of the upsampled matrix already, so that you know that you just have to fill in to those positions uh, such that you maintain the dilation. Okay. So you will be given that in your pseudocode, so you don't have to worry about the size of the upsampled matrix which you're referring to. So since you'll know the size of the upsampled matrix, you'll know how much to dilate in between, you'll know the exact positions where you have to place your gradient back into that matrix. Make sense?
Yeah, thank you.
Okay. There is a question on chat with stride, with divided by stride. Oh, maybe an answer.
That was an answer. Yeah.
Yeah. Okay, great. Any other questions? With forward or backward, anything? Okay.
Great. Should I stop the recording then?
Yeah.